Every natural language processing tool has to be evaluated, and language models have to be evaluated as well. What does it mean for a language model to be a good language model? In general, we say a good language model is one that is better at finding the good sentences and liking them more than the bad sentences. Or more specifically, we want to assign a higher probability to real or perhaps frequently observed sentences than ungrammatical or impossible or at least rarely observed sentences. So that's the goal of our evaluating a language model. Now we train the parameters of a language model on a training set. And we test the model's performance on data that we haven't seen. So we have some training data and some unseen data. This unseen data is called a test set, and we want it to be something that's not the same as our training set, totally unused, we've never looked at it before, and that will be a fair evaluation of our model. And then we'll need an evaluation metric that tells you how well does your model do on this unseen test set. So what are these evaluation models? The best way of comparing any two models, two language models A and B, is to put each model in a task. So we're going to build our spelling corrector or speech recognizer or MT system, whatever our application is that uses language models. We'll put our language model in there, and now we'll run our task, and we'll get some accuracy for the system running with model A, the system running with model B. Perhaps that's how many misspelled words are corrected properly if we're doing spelling correction, or how many words are translated correctly if we're doing translation. And now we just compare the accuracy of the two models. Whichever model has a higher accuracy is the better language model. So this is called extrinsic evaluation. We're using something external to the Ngram model itself and looking at our performance on that external task. The problem with this kind of extrinsic evaluation, it's also called in vivo evaluation, is that it's time consuming. In many cases, this can take days or weeks. For a modern machine translation system or a modern speech recognition system, running evaluations can often be extremely slow. So instead, what we sometimes use is an intrinsic evaluation, something that's intrinsically about language models themselves and not about any particular application. And the most common intrinsic evaluation is called perplexity. Now, perplexity happens to be a bad approximation to an extrinsic evaluation unless it turns out that the test data looks a lot like the training data. So generally, perplexity is useful only in pilot experiments, but it does help to think about the problem, and it's a useful tool as long as we also use extrinsic evaluation as well. So let's think about the intuition of perplexity. And like many ideas in language modeling, this dates back to Claude Shannon. So Shannon proposed, among many other things, a game about word prediction. How well can we predict the next word? So for example, we've seen sentences like, I always order pizza with cheese and our job is to predict the next word. So from this first sentence, we might say, well, a good language model might guess that we are likely to have mushrooms and likely to have pepperoni and maybe less likely to have anchovies because anchovies are somewhat less popular than mushrooms, and very unlikely to put fried rice on our pizza, and extremely unlikely, let's say, to have although people, I guess, do say and after the word and. And so how well the model predicts the actual words that occur is how good the model is. So a model on a sentence like the 33rd president of the U.S., we know the next word is very likely to be JFK or John or Kennedy or some word like that. So this is a pretty predictable case. Here we have, I saw anything could come next. So in some cases we're going to be much better at predicting the next word. In some cases, very much worse. But a good language model, on average, should do better than a bad language model. Now, it turns out that unigrams are very bad at this game. And if you think for a second, you'll realize why. So in summary, a better model of text, a better language model, is one that assigns a higher probability to whatever word actually occurs. If you can guess right the next word, you are a good language model. So the best language model is the one that best predicts an unseen test set, or assigns, on average, the highest probability of a sentence to all the sentences that it sees. If you give me a new test set, and I try using different language models to assign a probability to each of its sentences, the better language model is the one that says, oh, I knew that sentence was coming, and assigns it a very high probability. Now the perplexity, this new metric we're going to be using, is inversely related to probability. It's the inverse probability of the test set normalized by the number of words. Let's imagine our test set is a single long sentence, n words long. We compute the perplexity of this n-word sentence by taking the inverse probability, 1 over its probability, and then normalizing by length by taking the nth root. We take the nth root because otherwise, the longer the sentence, the lower the probability, since we're multiplying lots of low probability n-grams together. So we want a normalizing factor so we can compare test sets of different lengths. So just showing this another way, the perplexity of a string of words of length n is the nth root of 1 over the probability of the string of words. So by the chain rule, the probability of this string of words 1 through n is the product over all I of the probability of each word given the entire prefix beforehand. We're just using the chain rule here to rewrite the probability of a long sequence with the product of the probabilities of each word given its prefix. And then for bigrams, by our Markov approximation to the chain rule, we can estimate the probability of a sequence of words with the product of a bunch of bigrams. So the perplexity of a string of words according to a bigram model is the nth root of the inverse of the product of n bigram probabilities. So because of this inversion, minimizing perplexity is the same as maximizing probability. And this is important to keep in mind when thinking about perplexity. There's another intuition for perplexity, also based on Shannon. And this example comes from Josh Goodman. And this second intuition for perplexity relies on the idea that perplexity is the average, related to the average branching factor. Perplexity at any point in a sentence is, on average, how many things could occur next. And we'll see later this is related to the probability of the upcoming things, related to the entropy of the upcoming things. But roughly speaking, if I had 10 possible words that could come next and they were all equal probability, my perplexity would be 10. So for example, if I'm recognizing the 10 digits, then the perplexity of the task is 10. There's 10 possible things that could come next and I can't decide between them. If I have to recognize, if I'm building a speech recognizer for a switchboard phone service, and I have to recognize 30,000 names, then the perplexity of the names is 30,000 if they're all equally likely. But suppose a system has to recognize, let's say again, a switchboard phone operator, automatic phone operator, has to recognize the word operator, and that occurs a quarter of the time. The word sales, that occurs a quarter of the time. Or the word technical support, that occurs a quarter of the time. And then with 1 over 120,000 times each, another 30,000 names occur. So now we have to take the weighted average of all these possibilities of what could occur to compute, on average, how likely is any one word to occur. And now the perplexity is 54. So the perplexity, again, is the weighted equivalent branching factor. So let's examine this new kind of perplexity, the weighted equivalent branching factor, and show that it's the same as this inverted normalized probability metric. So let's take a sentence consisting of random digits. What's the perplexity of this sentence according to a model that assigns equal probability to each digit? So we'll see the perplexity of the sentence, this string of digits. Let's make it it doesn't matter how long it is. So we have a bunch of digits, and the probability of this bunch of digits, we'll call them digit 1, digit 2, through digit n. The perplexity by our first metric is -1, is the probability of this sequence to the -1 over n. And since we've said that each of these words has probability 1/10, and we're assuming a unigram probability, so that's the probability of 1/10 times 1/10 times 1/10 times 1/10, and so on. So that's that's 1/10 to the n, because there were n words, to the -1 over n, and as we can see over here, that's equal to the n's cancel. We get 1/10 to the -1, or we get 10. So by thinking about perplexity as the normalized probability of a long string, we can sort of see the intuition that the average branching factor, by normalizing for the length, we're sort of asking how many things can occur at each time, weighted by their probability. All right, so now perplexity in general, the lower the perplexity, the better of the model. So for example, here's where a training set trained on 38 million words, tested on 1.5 million words from the newspaper The Wall Street Journal, and a unigram model has a perplexity of 962. A bigram model has a much lower, much more accurate perplexity of 170, and a trigram model has even a lower perplexity. So perplexity, since it's modeling something like average branching factor or average predictability, the lower you get, the better you are predicting the actual data that occurs.